Let's take a look at the next chapter, chapter 11, input and output. Methods of supplying inputs and obtaining output values depend upon the input and output I/O devices connected to the CPU. They range from user inputting data in to move this out of the way. There we go. Move that down. Isn't blocking anything for the most part. But you could have a user input and data. You could have electronic equipment input and data. Could be the output is somehow driving the input. So there's a lot of different ways it can occur. It says ARM systems are embedded in a wide range of products used with many different I/O hardware systems. It is not possible to give a general description of programming methods to implement input and output. Only a few typical examples can be described. So don't think this is all encompassing. Operation of any I/O device, peripherals, depends on the design of the hardware circuits and often involves ensuring that sequences, CPU actions controlling them have a precise form. To meet hardware requirements, sections of a program that handle the I/O must sometimes be prepared in assembly language. Sometimes, when you're in computer science, the assembly language that you're looking at may not even be what you might think. For example, let's see if I can get this up and running. Close some of these items, maybe. There it goes. Had a lot of different applications open up for the previous class. And see if I can get back to that point. C drive. This PC. I know this is pretty small. Ignoring that fact, though, go to the show applications here. Type to search. I'm going to type in terminal. This I can make a little bit bigger. We'll see if I can remember the commands. That's an important part there. And nano test.c. And int main. Hopefully I'm remembering this right. And let's see, int sum. Sum is equal 3 plus 5. Return 1. Control O. Control X. GCC test.c-o. I'll make it test all uppercase. And doesn't like that. Oh, semicolon. Control O, enter. Control X to exit. GCC test.c-o test. GDB. I don't know if I need to put test here or not. Let me put test there. Maybe I do a load test. Test. Quit. Okay, let me go look at the document on that. Computer forensics. Just did it this morning. You think I'd remember. Disassemble. D-I-S-A-S. Okay. So GDB. Disassemble the one I just created, which is an all uppercase test. It doesn't like that. Test.c. Control X or XQ. Well, I got a test there. Maybe because I didn't do these options. Let me run that again. GCC-G-Z test.c dash F, wait a minute, not C, execute stack dash FNO dash stack protector. Okay, test.c-o test. GDB disassemble test. And let me read a little bit more about it. Okay, so go through, do all that. Okay, so you do GDB BOF, or in our case, our name. So quit that. And, okay, so done that. GDB test, all uppercase. And then after that, we want to disassemble main. Assuming I called it main. There we go. This is what I was talking about. Sometimes in programming, when you do have to look at some assembly language code, and this is for another class, it doesn't necessarily match what we've been showing in this class. But understanding what some of these options do, the push and pop, and doing a move and so forth, can help figure it out. So bring that over. Let me do a new window. So this is our disassembling our program here. So again, being able to understand the different pieces here. From this class, we've seen push, pop, move, so forth. So this should help you to figure out what's going on with it. Okay, it talks about how we ignored input and output earlier on. We just hard-coded values and so forth, and that's fine. Because at this point, we're just learning the basics of assembly language. Okay, small target boards are available for initial studies of ARM systems. These ARM-based microcontrollers, they incorporate I/O devices. Again, we don't have this available, so keep that in mind. So let's talk about simple I/O now. For simple hardware systems, each output device port belongs to either 1 byte or 1 word of memory to which data are written. The values written to an output port appear as electrical signals at the output connection points with separate signal connection for each bit. Input values are obtained in a similar manner by reading from a single specified location. The input devices must be designed to supply electrical signals for each input bit. They talk about the design aspects of the ARM for microcontrollers. Things you have to worry about. Configuration is performed using registers called special function registers. This tells us to examine the behavior of the output port after assembling and loading program 11.1. We start the simulator with the usual debug, start, stop, debug session. But before running the program, select peripherals, GPIO, slow GPIO. This will open a window showing values of individual bits of all the SFRs. Those are our special function registers associated with the I/O ports and also values at the port pins of the devices. The value is indicated by the box for a bit using blank if the value is 0 and checked if it's 1. Although we haven't put in program 11.1. Let's go into our UVision or MooVision. That's not a U, that's a moo. It's Greek letter. Okay, so do debug, start, stop, debug session. And now they're telling us to go into peripherals. And we don't have a GPIO. Yeah, let's see if they got somewhere other location. Or it could be because we haven't put that program in. So let's put that program in, then we'll take a look at it. Pin select 0 equals E00 to C000. IO pin, input output pin equals 0x E0028000. And off directory EQ 0x8. LDR SP equals 0x 4 3 zeros 1 and 3 zeros. LDR R1 equals pin select 0. Move R0 pound 0. Store R0 R1. Excuse me. LDR R1 equals input output pin. LDR R0 equals 0x 4fs. Store R0 R1 comma pound off dir. Move R0 pound 0. Next, store R0 R1. Add R0 R0 pound 1. LDR R2 equals 0x2000. Sub S R2 pound 1. And that was actually delay. Branch not equals to delay. Branch next. Program loops forever, so no ending mechanism required. And there's an end, but I have that down here. Okay, assuming I typed it in correctly, let's do a project, build target. 2 warnings. And still not there. Let's see where they moved it to. Oh well, I won't show that. There we go. Okay, this is on page 143. An example of a single output port using LPC 2102. Now this says controls the function of the 10 pins. So pin select 0 gives us that. I/O, actual output register address. It's right here. And register from the or offset of I/O dir. Pin direction register from I/O pin address. Come down here, we got stack at the RAM top. Stack not used, but always set it up. Point to pin control register. So set P0.0 to P0.15 as general. Purpose I/O, GPIO pins. And then we got our point to I/O pin. And it's at P0.0 to P0.15 as outputs. And using I/O directory or direction register. Initial output value, send output pins, increment output values. And then our looping. Grab a drink here. This is one piece of another program. It's subroutine. So saving off our return address, so we know when we're returning where to go back to. So that's what this command does. And this is when we're going to the turn on. And subroutine turn on port bit numbers 0 to 15 passes parameter. Parameters forced to be in a range of 0 to 15. An alternative is check it and return an error indicator if it's out of range. Okay, so this forces the parameter to be in range. Point to IO pin. Address of the copy of the output. Mask for 1 bit. Move mask to required position. Get value currently at the port. Force required output bit to 1. Send output pin, save, copy the output, and then return. And alternative pattern output method. I don't think we'll go over that. Now, serial I/O. Connecting a processor system to an I/O device using one electrical circuit for every bit of input or output data is simple but inconvenient and expensive if the device is some distance from the CPU. An alternative is to send data bits one after another using a single circuit. This is serial communication. The bits are in series and time. There are many serial systems, and some of the most easily implemented that is built to the standards. Systems of these standards are often called RS-232, which you probably heard about that, or EIA-232. You probably haven't heard about that. Ones as they were developed from the single EIA standard. Though the standard is no longer commonly used in consumer products, it's still used in industrial systems. Standards were developed to make connections between computer systems and remote terminals using the telephone system, modems. This is what we're talking about. We're talking about pins and so forth. This is where you have this kind of communication. So 9-pin socket connected to the PC, 9-pin plug connected to the target. I don't see serial a whole lot anymore in computers. You see them a lot of other places. Talks about the typical UART SFRs. List does not specify any specific UARTs. Wish we could load that up on MoveVision. Again, we're programming this to where it works with the pins. So it controls function of the 10 pins. Here sets the P0.0 as TX0 and P0.1 as RX0. UART 0 base, also buffers and control register. Got our offset here. Line status register, the LSR. For 8 bits, no parity, 1 stop bit. This sets U0, sets up all SFRs for US ART 0 operation. Again, here's our storing off our return path, and here's us going back. Pattern to enable RxD0 and TXD0. Point to pin control register. Get existing pin control patterns, set pins, mask. There's output one character using serial port 0. Corrupts R1 and R2 is allowed by the BPCS. Again, storing off where we came from. This is causing us to go back. Here I'm loading in the base address for the UART. Get the default status, or get the current status for UART. Check for transmit buffer is empty. Branch on equal. I'm not sure if I see W. Oh, here. Branch on equals here. Ensure callee is only one set byte pattern. Low transmit buffer, so forth. Here we got a simple switch input circuit. Keyboard is a set of spring-loaded switches that close when pressed and spring open when released. When a switch is connected directly to a simple input port, a program can determine the switch position by reading the input. Two switch positions provide input for values of 0 and 1. The values for the open and closed positions depend on the circuit construction. Example of a light switch input signal. Bounce typically lasts about 5 milliseconds. Here we have a start. This is a flowchart of sequence detect a keyboard switch press. Is switch open? No. Then it keeps going up here. If yes, wait about 5 seconds and then ask, is the switch open? Yes. Then you come down here, is switch closed? Wait about 5 seconds. And you switch closed again, asks. And then if it is, then key is pressed. Well, there isn't a whole lot in that chapter. We've got 2 more weeks, 2 more chapters I'm gonna cover. Never really haven't been able to cover chapter 14. Time for me to put the our final project out there. So we go ahead and do that now. project from chapters 11 to 14. Complete 2 problems out of each chapter. And turn in the answers and any code. So it's your choice. This is going to be due on May 3rd at 5 p.m. Won't take it later than that. Got to have time to grade it, so I need that weekend to grade it. And I'll quit showing it this time at 5 p.m. And that'll be our final project. So in turn, that means you turn in 11, 12, 13, 14. 2 problems out of each, you turn in 8 problems total. I'll go ahead and stop the recording there.